Step 7, describing segments. In addition to binary and multinomial logistic regression, there are also other regression or classification methods possible to predict a binary or categorical variable. And what we are looking at here are tree-based methods. They construct trees using the descriptor variables such that the final nodes of our tree are as pure as possible and allow for a good prediction of a specific category. There are different implementations for trees available in R. What we will be using here is the implementation of conditional inference trees available in package PartyKit, which you need to install first in order to be able to use it. And the conditional inference trees in R are fitted using function ctree from package PartyKit. It also has a formula interface where we specify what's our dependent variable. Here it's a binary variable indicating if a respondent is in segment 3, yes or no, and we want to predict it using any of the descriptor variables available in that data frame here. And these are those which we consider as splitting variables in our tree construction algorithm. So the output here is the model formula. So these are all the variables which we considered as splitting variables, where this is the final tree we obtained. So this is a description of the tree. We have a first node, which is the root node, that contains all observations. These observations are now split into two child nodes, number 2 and 3, using a splitting variable vacation behavior. So this was the one selected as the best splitting variable among all possible ones, using, in the case of conditional inference trees, a test for independence and inspecting the p-value. Having selected the variable, the best split point is selected such that also the two sample test has best performance to differentiate best between the two groups. And we see node 2 is already a terminal node in the sense that it's not split any further. This is a terminal node, and information for terminal node is how big is it, how many observations does it contain, what's the predicted value for that node, and what's the error we're. So this is indicating we would predict it's not a member of segment 3, and this is the error we're making, 31.5%. Next, we look at this node 3, and this one is split further into node 4 and 5 using splitting variable obligation, and the split point is 3.9. And here we have the number of observations in each node, what would be the predicted value, so that's majority vote, and what's the error in that case. And here's the summary of the tree size, how many inner nodes and terminal nodes do we have. So that's the print output. Often it's better to look at the visualization of the tree because it's easier to see what's going on. So this is our root node. It splits vacation behavior in these two groups, and if we follow that, we see this now contains observations where the vacation behavior score is less than 2.2, and we see here in the terminal nodes the visualization gives us the distribution of 0s and 1 in that node. So we see this is the node, all of the terminal nodes, the node which has the highest proportion of members of segment 3, whereas this is the node with the lowest proportion of segment 3, and it contains respondents who have high vacation behavior score and also high obligation score values. And the p-values, the p equals here, is the p-value of the independence test we performed. As an alternative, we look at predicting segment membership for segment 6 using exactly the same interface, and then we add some controls. So we can control the growing of the tree in the sense when do we stop. And stopping criteria are different. Once we say if we perform an independence test and the p-value gets too large, we will stop. So this is the min criterion here. This says for which p-values or 1 minus p-values in effect should we proceed. And then we might also be interested in only constructing nodes to have terminal nodes of a certain size. And this is the min bucket, which says we only want to consider nodes which lead to terminal nodes containing at least 100 observations. So we don't want to have a too fine-grained solution. And there, if you want to have a look, C3_control allows you to specify a lot of other arguments for how long would you proceed, which splits do you want to consider, and so on and so forth, or even which test statistic do you want to use for your independence test. This is that tree. And we see here we have grown it much larger. So we have here the first split is obligation, then this one is split by age, then obligation comes again. So any of the splitting variable once used is reconsidered again. And here we have the relationship status. So we can, following this, we get a rule of who are the respondents contained in that node 5, and here they have a very low probability to be from segment 6. So this is a rather pure node with respect to not being in segment 6. And if we have a categorical variable as a dependent variable with more, not a binary, but more than 2 levels, we can just use that as a dependent variable. We also want to consider all of the descriptor variables again, and this is what the final tree looks like. Hasn't changed much, so the output looks pretty similar. Let's look at what the plot does. The plot changes for the categorical variables in the way what kind of plot is used for the terminal nodes to reflect what is the distribution of the dependent variable looks like. The observed relative frequencies of observations in that node for the 6 segments. So we could look, hopefully, so what we're aiming for is to get these nodes as pure as possible to contain only one single segment, and in that way we want to be able to follow through splitting the observations along, for example, obligation scores. Are we able to identify a group of respondents who are exactly from one segment?